Welcome to the deep dive.
Yeah.
Today, we're going deep on machine learning architecture.
Ooh, fun.
Yeah, it's going to be good. We're looking at a framework called the 4+1 view model, which is basically like a blueprint for building and evaluating those ML techniques.
I like that blueprint analogy.
Yeah, it kind of sets it up nicely to think about it visually, right?
Totally.
I've got a stack of research and articles here, and luckily we've got our expert here to help us break it all down.
Happy to be here.
I think this is perfect for anyone who is new to ML because it really lays out 5 key considerations when you're thinking about it.
Yeah, and it's a really nice way to approach this because it goes beyond just like the hardcore technical stuff.
Yeah, for sure.
Yeah.
So first up, we have scenarios like, how do you figure out which type of machine learning is right for the problem that you're trying to solve?
Right, because it's not one size fits all.
Definitely not.
And then, of course, there's accuracy. What does good even mean?
And we've got to think about complexity too, right?
Yeah, that sweet spot between power and practicality. And then, of course, we have to think about interpretability. We have to peek inside that black box.
Right, see how the decisions are made.
Totally. And then finally, there are the operations, taking machine learning from just like a fun experiment to a system that actually works in the real world.
Right, so let's dive right into those scenarios.
Yeah.
I think a lot of people, when they think of ML, they think, oh, it's kind of like a one-size-fits-all thing, but it's so not.
Absolutely not. It's way more like having a toolbox full of very specialized tools.
Okay, I like that.
So you're not going to use a hammer to tighten the screw, right?
You're going to strip that screw.
Exactly. And it's the same with ML. Our sources outline several categories, supervised, semi-supervised, unsupervised, and reinforcement learning.
Okay, so within all of those, do we have even more categories?
We do, even more. You've got types like classification, regression, clustering, and a whole bunch more.
Okay, so maybe give us an example, because that's a lot of jargon to just throw out there.
Sure. So let's imagine that we're building a customer service chatbot. One part of this might use supervised learning, specifically classification, to figure out what the user actually wants.
Their intent.
Exactly. Like, are they asking a question? Are they making a complaint? Are they trying to order something?
Right.
But then for the actual dialogue flow, we might use reinforcement learning where the chatbot learns through trial and error how to respond in a way that, gets the user what they want.
Interesting. So that chatbot is using a couple of different learning styles.
Exactly.
Wow. That's really interesting. Now, something that I found kind of surprising in the research is that deep learning isn't always the best choice.
Yeah, right. There's definitely this misconception that deep learning is, kind of the magic bullet for all ML problems.
The end-all be-all.
Right. But our research actually points out that for structured data, like what you would find in a spreadsheet, simpler models often do better.
Like decision trees?
Exactly. Deep learning is great when you have tons and tons of unstructured data, images or text, where it can just automatically pull out those complex features. But with structured data, a lot of that feature engineering is done, manually by a person.
So it's really about picking the right machine learning approach. It's not just about the problem. It's about the data that you're working with.
That's a really good way to put it.
Awesome. Okay, let's move on to accuracy, because I think most people, when they think of an accurate model, they think, oh, that model is right all the time.
Mm-hmm.
But these sources suggest it's more complicated than that.
For sure.
So what is this bias-variance trade-off all about?
Yes. That's a key concept when we talk about ML accuracy. Simple accuracy is important, but there are all these different kinds of errors.
Okay.
So bias is basically how far off your model's predictions are on average.
Okay.
So think of it like if you're aiming at a target and you hit the same spot every time, but it's off center.
Consistently wrong.
Yes,
Okay.
Exactly. That's high bias.
Okay.
Variance, on the other hand, is like how much your predictions jump around when you make small changes to the data.
Okay.
So you might hit the bullseye sometimes, but then other times you're way off.
You're all over the place.
Exactly.
Okay, high bias is consistent, but wrong, and high variance is all over the place.
You got it.
So what's like the ideal situation then?
Well, ideally, you want a model that is low bias, so it's on target, but also low variance, so it's consistent.
Right, so how do you get both?
Well, the challenge is finding that balance, and the way you measure accuracy also matters a lot, because in some cases, a false positive is way worse than a false negative or the other way around.
Oh, that's interesting.
It all depends on what you're trying to do.
Can you give me an example?
Yeah, so if you're building a medical diagnostic tool, obviously you're super concerned about false negatives.
Missing a disease.
Exactly. But if you're doing something like email spam, filtering, a few false positives, it's really not that big of a deal.
Yeah, that makes sense. Okay, so to really kind of dig into that accuracy,
Yeah.
we need to look at this thing called the confusion matrix, right?
We do. That's a great way to visualize how well your model is actually doing.
Okay.
It basically breaks down the different types of predictions.
Okay.
So let's think about our spam filter example. The confusion matrix shows us how many emails were correctly classified as spam, how many were correctly classified as not spam, and then all of the errors.
Like the spam that got through and the good emails that got flagged.
Exactly.
It's like a detailed report card for the spam filter.
I love that analogy.
Cool. So that helps us choose the right accuracy metric that really matters for whatever we're using this system for.
Yes. And speaking of choosing the right approach, sometimes simpler is better. And that brings us to our next topic, complexity.
Okay, so is a more complex model always better? Our intuition might tell us yes.
Right.
But the research that we have here suggests otherwise.
Totally. Sometimes a simpler model is actually going to be better because complex models can be really hard to understand and explain.
Right, it's like a black box.
Exactly. And that lack of transparency can be a big problem, particularly in things like medical diagnoses or, loan approvals where the stakes are really high.
Right, it's kind of scary to think that something's making decisions, but we don't know why.
Yeah, and simpler models can be easier to explain, and sometimes that clarity is worth, sacrificing a little bit of performance.
Especially if you have to justify that decision to somebody.
Right. Plus, complex models are also more prone to overfitting.
Now remind me what that is again.
Overfitting is basically when your model memorizes the training data instead of actually learning the underlying patterns.
Okay.
So it might do amazing on the data it's already seen, but then completely fail on new data.
It's like that student who crams for the test
Yeah.
and they can't actually apply the information.
Yes. Perfect analogy. So it's not just about accuracy. You also have to think about how well the model generalizes to new information.
Right. And I'm assuming that complex models also take more computing power and time to train.
Absolutely. They need more processing power. They take longer to train. So there's a very practical element here as well.
So finding that sweet spot like we talked about.
Exactly. The Goldilocks Principle. Not
Yeah.
too simple, not too complex. That's right. And, sometimes reducing complexity can actually make your model more accurate because it's less likely to overfit.
Okay, so how do we do that?
One way to do that is through something called dimension reduction.
Dimension reduction.
Yes. It's kind of like if you take a super high resolution image and you compress it, but you're not losing too much detail.
Okay, so how does shrinking the data make the model better?
So sometimes your data has just a ton of redundant or irrelevant information.
Right.
And dimension reduction techniques can find ways to represent that data with fewer variables, but still preserve those important patterns.
Interesting.
So that can simplify your model, make it faster to train, and make it less likely to get kind of bogged down by noise in the data.
So you're basically just tidying up the data.
Exactly. You're giving the model a cleaner set of information to learn from.
Okay, I like that. And this kind of ties into our next topic, which is interpretability.
Yes. Because if your model is simpler, it's easier to understand what it's doing.
And that's super important as machine learning is used in more areas of our lives.
Totally. We want to know why a model is making the decision it's making.
Yeah, especially in areas like healthcare and finance.
Right, where the stakes are very high.
Right.
And there are tons of different techniques for making models more interpretable.
Like what?
So some techniques focus on building models that are inherently explainable, like decision trees.
Okay.
Those tend to be simpler, but they might not be as powerful as the more complex approaches.
Right.
And then you have techniques that try to explain those complex models after they've been trained.
Right.
Things like SHAP values, which basically help us understand how much each feature contributes to a certain prediction.
Okay, so kind of like figuring out which ingredients in a recipe are the most important.
Exactly. So the more interpretable a model is, the more we can trust it, the more we can make sure it's not biased. And, if things go wrong, we can actually figure out why and debug it.
Right, so we've talked about choosing the right type of model, understanding accuracy and complexity, peeking inside that black box of interpretability. But what happens when we actually want to take our ML model from the lab and put it into the real world?
Yeah, that's a great question. That's where operations comes in and this whole world of MLOps.
So tell me about that. What is that all about?
MLOps is all about taking ML from that fun experiment to something that works reliably in the real world.
Okay.
It's about bridging the gap between development and deployment, and there are a ton of things to think about when we're talking about MLOps.
Okay, so what are some of the highlights?
So one key idea is continuous integration and deployment,
Okay.
also known as CI/CD. It's all about automating the process of updating and deploying models as new data comes in. Because, in the real world, data is constantly changing and your model needs to keep up.
So it's not just about building a model and forgetting about it.
Not at all. It's an ongoing process, and part of that process is continuous training. Your model needs to be retrained regularly to stay up to date and to prevent this thing called data drift, where the data that you trained your model on originally starts to look really different from the data that it's seeing in the real world.
Like it's getting out of date.
Exactly. You got to send your model back to school.
To learn the new trends.
Exactly.
Okay, so continuous learning is key. What else do we have in MLOps?
Well, another really important aspect is continuous monitoring.
Okay.
You got to keep an eye on how your model is doing out in the wild. You got to keep track of things like accuracy, speed, how much computing power it's using.
Right.
And if you spot any problems or, the performance starts to drop, then you got to take action and fix it.
So it's like having a health tracker for your model.
Right, totally. And something that I think is super fascinating is version control and lineage tracking in MLOps.
So you mean keeping track of like all the changes to a model over time?
Exactly, like who made what changes and when.
Okay.
It's basically like a detailed history of your model's evolution. And this is super important for debugging, reproducing results, and auditing.
Right. So if something goes wrong, you can kind of go back in time and see what happened.
Exactly. So basically, MLOps is all about making sure that your models can adapt to new data, they keep learning, and they actually behave themselves in the real world.
It sounds like a lot to keep track of.
It definitely can be, but it's super crucial for making ML work outside of the lab.
Okay, so we've covered so much already. We've talked about choosing the right type of model, understanding accuracy and complexity, peeking inside that black box of interpretability, and now we've tackled this operational side of things with MLOps.
It's a lot, but it's all connected.
It is. We've basically laid out this blueprint for building and evaluating ML techniques.
I think the 4+1 model is a great framework for thinking about machine learning in a really comprehensive way.
And I really like how it emphasizes, not just the theory, but the real-world aspects.
For sure. Making it work in practice.
Yeah, exactly. Now, before we jump into some listener questions, I'm curious, what really stood out to you? What got you thinking? Was it, the idea that deep learning isn't always the best choice, the importance of data, or maybe this concept of continuous learning with MLOps? What really got your gears turning?
For me, it's how this whole framework highlights that we need to understand both the what and the why of machine learning. It's not enough to just build models that make good predictions. We need to be able to explain how they work, make sure they're being fair, and that they work reliably in the real world.
Absolutely. It's not just about the technical side. It's about using that power responsibly.
Exactly.
All right. Well, let's take a quick break, and then we'll be right back to tackle some of those listener questions. Okay, so we're back and ready to dig into some of these great listener questions.
Yeah, I love listener questions.
Me too.
Yeah.
All right, so first up is a question from Alex, who asks, you mentioned the confusion matrix earlier, but I'm still a little confused on what that is. Can you explain it like I'm 5?
Okay, Alex. Imagine that you're teaching a robot how to sort blocks into 2 different buckets.
Okay.
One for red blocks and one for blue blocks.
Okay.
The confusion matrix is basically like a scorecard that tells you how well that robot is doing.
Okay.
It shows you how many blocks it put in the red bucket correctly, how many it put in the blue bucket correctly, and then it also shows you the mistakes.
Okay, so where it messed up.
Exactly. So how many red blocks ended up in the blue bucket and vice versa.
So it's not just about the overall accuracy, right? It's about understanding different types of errors.
Exactly. And that helps us figure out, is the robot just bad at sorting blue blocks? Or is it having trouble with red blocks? And that can help us, figure out how to improve it.
Okay, I like that analogy. Now, let's say our spam filter is doing a pretty good job overall, but we notice from the confusion matrix that it's letting a lot of actual spam slip through.
Yeah, that's a problem.
Yeah, because spam is bad.
It is. So that's where recall comes in. Recall basically tells us how good the model is at catching all of the positive cases.
So in this case, all the spam emails.
Exactly. If recall is low, we know that we need to tweak something because we're probably missing too much spam.
And on the flip side, if our spam filter is, flagging tons of legitimate emails as spam, that's annoying too.
Definitely. Nobody wants to miss an important email. And that's where precision comes in. Precision measures how many of the positive predictions were actually correct.
Okay.
So if the precision is low, it means that our model is kind of crying wolf a lot, and we need to adjust it to reduce those false positives.
Okay, so the confusion matrix helps us see all the different errors, and then metrics like precision and recall help us zoom in on the areas that need work.
Yes. Great summary. All right, what's next?
This next question comes from Sarah, and it's about complexity.
Yeah.
She asks, you talk about finding that sweet spot between model complexity and performance, but how do you actually know when a model is too complex?
That is a great question, Sarah. It's a lot easier said than done, right? There are a couple of warning signs to watch out for, though.
Like what?
Well, one is overfitting, which we talked about before. If your model is doing amazingly well on the training data, but then it completely fails on new data, that's a huge red flag. That it might be too complex and that it's basically memorized the training set instead of actually learning something useful.
Right. It's like cramming for the test, but then failing the exam.
Exactly. Another thing to think about is interpretability. If you're really struggling to understand why the model is making the decisions it's making, that might be a sign that it's just too complex and that a simpler model would be better.
Right. Sometimes that clarity is worth a little bit less performance.
For sure. And we also have to think about practical stuff, like how long does it actually take to train this complex model, and how much computing power does it need to run? You know, if it takes weeks to train or it needs a supercomputer, that's not really practical for most applications.
Yeah, that's a good point. So it's not just about theoretical performance. It's about, what works in the real world.
Yeah.
All right. Next question is from David, who asks, you talked about MLOps, and I'm really interested in this continuous learning idea. Can you give us some examples of how models are retrained in real life?
Sure. So let's say you have a model that predicts customer churn.
Okay.
You know how likely a customer is to stop using your service? You train this model on data from the past year, but now it's 6 months later and customer behavior might be completely different.
Right.
Maybe a new competitor popped up or your company launched a new product or feature.
So the model's getting kind of stale.
Exactly. To keep it fresh, you need to retrain it on the new data.
Okay, so just add in the new data.
Well, you can do that,
Yeah.
or you might need to do like a more comprehensive retraining where you actually adjust the model's parameters based on all the new information.
Okay.
And how often you do this really depends on how fast the data is changing and how important it is for your model to be up to date.
Right, so if it's like stock prices that change every second, you need to retrain constantly.
Yeah, exactly. But for something like our customer churn model, retraining once a month or even once a quarter might be just fine.
So it all depends on the situation.
It does. It's all about adapting to the data.
This next question is from Emily, and she asks, you mentioned that MLOps requires collaboration between data scientists and software engineers. What are some of the challenges in bridging the gap between those two roles?
That's a great question, Emily. It's definitely something a lot of companies struggle with because traditionally those two groups kind of work in silos.
Separate worlds.
Totally. They have their own tools, their own processes, and even their own cultures.
So bringing them together can be tough.
It can. One challenge is just communication. Data scientists use all this technical jargon that software engineers might not understand and vice versa.
Lost in translation.
Right. And they also often have different priorities. Data scientists are all about model accuracy and how well the model performs. But software engineers are thinking about things like scalability and reliability.
Making sure the system doesn't crash.
Exactly. So you really need to have a shared understanding of what you're trying to accomplish and how everyone contributes to that goal.
Right. Everyone's working towards the same thing.
And then there are the practical challenges, like making sure that all the different tools that everyone uses can work together.
Yeah, because data scientists use special tools for building models that might not work with the tools that software engineers use for deployment.
Right. So you have to find tools that can span that whole ML workflow and actually help those teams collaborate.
So it sounds like a lot of communication, a lot of collaboration, and maybe even some compromise to make MLOps work.
Definitely. But when it works, it's amazing. It's about combining the creativity and the analytical skills of data scientists with the rigor and the discipline of software engineers.
Best of both worlds.
Exactly.
Okay, let's squeeze in one more question before we wrap up part 2. This one comes from Michael, who asks, can you talk more about the importance of monitoring and feedback in MLOps? It seems like it's not enough to just deploy a model and call it a day.
Absolutely, Michael. Deploying a model is just the beginning. It's like launching a rocket into space. You don't just fire it off and hope for the best.
Right. You've got to make sure it's on course.
Exactly. You got to monitor it constantly. You got to make adjustments. You got to collect data to make sure it's actually doing what it's supposed to do.
So what are we monitoring when we're talking about these models?
Well, we're looking at things like model accuracy, prediction latency, how long it takes for the model to actually make a prediction, and how much computing power it's using.
So if something looks off, we have to fix it.
Right, and that's where those feedback loops come in. We got to take that monitoring data and use it to make the model or the system better. Maybe we need to retrain the model on some newer data or tweak some of the parameters, or maybe we even have to go back to the drawing board and rethink our whole approach.
So it's a constant process of learning and improvement.
Exactly. And that feedback loop is essential for making sure that our models are actually useful and reliable in the ever-changing real world.
All right, great. Well, that's a wrap for part 2. We had some really great listener questions.
Yeah, they were good ones.
We've covered a lot of ground, but we have one more part to go. Let's take a quick break, and then we'll be right back for the final part of our ML deep dive. And we're back for the final part of our deep dive into a 4+1 view model of machine learning.
I can't believe we're already here. Time flies when you're having fun with machine learning, right?
Right. Okay, so we still have a couple more listener questions that I want to get to before we wrap up.
Sounds good.
So this one comes from Jessica, who asks, I'm new to machine learning, and I'm feeling a little overwhelmed by all the different algorithms out there. Is there a simple way to kind of categorize them?
That's a great question, Jessica, and I think a lot of people feel that way when they're first starting out. You know, it's like walking into a huge library for the first time and you have no idea where to even begin.
Right.
But just like books can be organized by genre, ML algorithms can be grouped by, you know, their learning style and the tasks they perform.
Yeah. Okay, so we talked about supervised learning, unsupervised learning, and reinforcement learning as like the main categories.
Right. So within supervised learning, you have algorithms that are specifically for classification.
Which is like sorting things into groups.
Exactly. And then you have algorithms for regression, which is about predicting a continuous value.
Okay, so give me an example.
Okay, so predicting whether an email is spam or not, that's classification.
Okay.
But predicting the price of a house based on its features, that would be regression.
Gotcha.
So supervised learning is all about learning from data where we already know the answer.
Okay.
And then we have unsupervised learning where the algorithm has to figure out the patterns on its own without any labels.
Right.
So clustering is a good example of that. Like, let's say you have a bunch of customer data and you want to group the customers who have similar buying habits.
Okay.
The algorithm can figure that out without you telling it, you know, what those groups should look like.
So it's like the algorithm is a detective trying to find the clues.
Yeah.
Exactly. And then there's reinforcement learning, which is a little different. This is where an agent learns through trial and error in an environment.
So it gets rewarded for good decisions and penalized for bad ones.
Exactly. Like, imagine training a dog, but instead of a dog, it's a complex algorithm.
That's a funny image.
Right. And this type of learning is being used for some really cool stuff, like self-driving cars and, you know, making stock trades.
Wow. Okay, so we've got supervised, unsupervised, and reinforcement learning. And then within those, we have specific algorithms for different tasks like classification and regression.
Exactly. But don't worry too much about memorizing every single algorithm right away. You know, as you work with machine learning more, you'll start to get a feel for which ones work best for different situations.
Okay, that makes sense. All right, next question comes from Mark, who asks, you've talked a lot about data quality, so can you give us some tips for actually ensuring data quality in real-world ML projects?
Great question, Mark. Data quality is so important. You know, it's like building a house on a shaky foundation. The whole thing is going to fall apart.
Right, garbage in, garbage out.
Exactly. So the first thing you have to do is really understand your data. Where is it coming from? How is it collected? Are there any known problems or biases?
Okay.
Once you have a good handle on that, then you can start thinking about cleaning and pre-processing the data.
Right, and we talked about that earlier.
Yeah.
What are some of those common techniques for getting the data ready to train a model?
So one thing you'll probably have to do is deal with missing values.
Okay.
Maybe you can fill those in based on other data points, or maybe you just get rid of those rows or columns altogether.
Okay.
And then there's feature scaling, where you adjust the range of your features so they're all on a similar scale.
So they have an equal chance of influencing the model.
Yes. And then there's feature engineering, which is super interesting. This is where you get to create new features from the existing ones.
So this is where human expertise comes in.
Absolutely. You're using your knowledge of the problem to pull out insights from the data that the model might not see on its own.
Okay, so it's kind of like guiding the model a little bit.
Exactly. And it's a process. You know, you might try something, see how the model does, and then go back and refine those features based on what you learn.
So data quality is a journey, not a destination.
Well said. All right, well, we've come to the end of our deep dive.
I know. I can't believe how much we covered.
We really explored this 4+1 view model as a blueprint for understanding machine learning.
We talked about choosing the right model, understanding accuracy and complexity, looking inside that black box, and making sure our models can actually work in the real world.
Hopefully our listeners are feeling a little bit more confident about diving into machine learning now.
Yeah, it's a complex field, but it's also incredibly exciting and powerful.
I think the key is to not get overwhelmed. Start with a solid framework, ask good questions, and never stop learning.
That's great advice. Thanks for joining us on the Deep Dive.
That was my pleasure.
And until next time, keep learning and keep diving.